The convention in terms of the symmetry of the barrier, or this beta, if you remember, we will see that, which is called symmetry coefficient. And the way I define it in the lecture is something that we can call, it's a matter of convention, but this is called Schmitt's convention, right? Yet, as you will look some other derivations of the same equation, some of them actually follow Bart's convention. So there is a Schmitt's and Bart's convention. This is what I've done in a class. What you're going to do in class is a Bart, as a homework, is a Bart convention. So Bart convention is homework. And what it really means is that you're going to derive in detail, like we did in class, using the same steps and everything, more or less same procedure. But the energy diagram will look a little bit different than the one I used. Okay. Now, how different that looks like? Well, if we take a situation with no electric field, this is going to be reduced. State, this is oxidized state. And then, as you remember, we defined activation barrier, or energy of the activated complex, which is here. As delta G naught, and then for cathodic reaction, which we described, we said it's a delta G hash naught cathodic, because this is from the level of the energy of the reactants up to the height of the barrier. And then we also defined delta G hash naught anodic, which is again the height of the barrier for anodic process when we are actually oxidizing. We use this, it's coming back here, okay. I'm just reminding what we have done now that we introduced this term here, which is some delta G, but according to thermodynamics is equal to minus NFE, which belongs to the field across the interface, right? And so I'm just gonna get rid of this for a second. And then this new state will be shifted as we introducing delta G, that is this term here. It will be going like this. And so if I extend this here, there will be new activation energy of the new reaction. And in this case, here, this will be delta G hash, just cathodic, and this will be just delta G hash anodic, okay? There's no not, because now it's not only chemical, but electrochemical, and that not thing removed. Now, what's the difference in what I'm trying to force you to do? If you look at the previous state, right? This level, and we said that the height of the barrier due to the introduction of the potential across the interface changes, and I labeled this difference here as beta and F and minus, because we assume this is positive, delta G is positive, so that basically must be minus some potential, right? This is what I used in convention. What you're going to do now, you're this convention, which is a Schmickler's convention, you're going to say this is your beta minus beta n, actually f e, and this thing here is minus 1 minus beta and f e, alright? Okay? And so now having this as an extra term that increases the height of your barrier, you're going to go through the same steps and derive a bottle-warmer equation that uses this notation, or basically convention, and it's basically fundamentally the same thing. What you're going to get is basically bottle-warmer equation in the end, that is going to be still equal I current density is equal I naught exchange current density. We're going to talk about this today a little bit more times. Now, here, what you're going to have is E to the 1 minus beta RT, NF over RT minus E to the minus beta NF over RT. Here's our potential, here's the potential. And this is basically what you're supposed to derive. The difference between this shape of bottle warmer and the one we derived is that here, which this represents the anodic contribution, this is the cathodic contribution to the rate, net rate. In our case, here was beta, and here was minus and then 1 minus beta. Now you can get this reversed by just following the same steps as we did in the class, one by one. Nothing new there, just look what I've done in the class and just with the algebra the way that it's supposed to be done, okay? And the one important thing is that then the current density, what you're going to get as a definition will be NF KC1 minus M, concentration of the oxidized species 1 minus N, then Ka N, excuse me, 1 minus beta, sorry, 1 minus beta, Ka beta, and then concentration of the reduced on beta. Okay, so this is going to be the definition of your exchange current density. So you should get this, you should get that by using the same step we did last time. That's your homework for the next Wednesday, right? I want this in handwriting legibly now so I can follow the steps you've done and make sure that you have mastered every step in a way that we've done in the class, okay? You will have tonight accessibility to the recording, so I don't think this is something difficult, but I want you to go through the same thing because this is the learning curve here, okay? Now, having said that, let's go discuss where we stopped last time. Let me just give you an idea in terms of the units again. So we said that current density is equal I naught. Then in Schmickler's, so I'm following what I have done, right? So this is what you need to do, but I'm following the original way I derived using the Schmickler's sign convention, right? And so this is E to the minus, to the beta, and F beta over RT minus E to the minus 1 minus beta and F over RT times beta, which is over potential. Remember, we defined that potential is equal over potential plus E equilibrium, and then when we were doing our thing, you know, this was put here instead of the E minus E equilibrium, etc. So I'll talk about this in the next step in more detail. Okay. Now, if you look the your notes from the last time you current density E naught, because the definition similar to this one, it's NF times Kc on beta times K on 1 minus beta times concentration, surface concentration of the steady species on beta and times reduced species of 1 minus beta. Okay, so this is your I naught. Okay, so obviously, just for the sake, I say it's current density, but let's verify. So, what we're really talking about in terms of the unit. You remember before this term Kc or Ka, I said it's in the form of some frequency multiplying some exponents, etc. Not to repeat myself. So this frequency here, term, has the same unit as these constants. And if you look here, basically, the unit for current density is equal to, what's the unit of the Faraday's constant? It's a charge of the unit per mole. So it's Coulomb per mole, right? So we're gonna write Coulomb per mole times, and then unit of the Kc and Ka is what? Is frequency. So it's a hertz or 1 over second, right? So I'm gonna write second minus 1 on beta times second minus 1 on 1 minus beta. Then here we have concentrations, but as you remember, we talked about these concentrations, and we talked about, because of the current, or actually reaction happening in the interface, those are surface concentrations, right? So the surface concentrations is basically mole per centimeter squared, let's say, on beta times mole per centimeter squared on 1 minus beta, right? So if you do the math, second on beta times second 1 minus beta, this beta drops, right? And here the same thing, and so what you end up having here is the mole multiplying is going to be basically just a mole per centimeter square, and this is going to be second minus 1. So in the end, what you're really having is the column centimeter square times second here. Column per second is amp per centimeter square. More common thing is that we use milliamp per centimeter square for the current density, okay? Fundamentally, current density, which is the expression that gives you good, is talking about flux. Flow per unit area of charge, material, whatever, is the flux. Now, in this particular case, the difference, whether you're talking about the flow of moles per unit area, second, is in this term here, NF, because certain charged species in number of moles has this much coulombs, right? So we're still talking about the flux like in the normal case. Okay, so that's important for you guys to appreciate that this expression gives you current density, okay, which is the flux, right? Now, another thing that I want to talk about, but this is really a Mickey Mouse stuff, is that once you know the current density, you can go from current density to flux by dividing the current with NF, right? Which is going to give you fluxes in moles per centimeter square second, right? Then, from flux, for example, if you do some manipulation, you can come up for a certain time how many moles per centimeter square you get. And if you know the area of the electrode, then you multiply all that, you're going to end up with how many moles you have. And if you have molar mass, you're going to end up what kind of a mass you got deposited, right? And if you got that, you can also go back and say this flux could be represented also as a rate, which is the nanometers or centimeters per second, etc., etc. How you go into one of these and so on will be topic of your homework, right? But what I'm trying to explain to you is that all this is a subject of the Faraday's law. And I'm not going to teach Faraday's law because it's a trivial, but the convenient thing for you guys is to play with different expressions of this flux of current density by multiplying with certain constant to get expression for the rate in nanometers per second, for example, or get the expression for mass flow in kilograms per second, or etc., etc., etc. Right? So that's going to be a subject of your homework, but so you understand where I'm coming from. Okay. So this is your homework. This is something that we just started, continuing discussion from the last time. Now, let's go discuss a few more things related to the Butler-Warner equation, which is here. You can see it's on the very top over here, but what I want to say is that if you plot, let's say if this is coordinate system, and let's say this is our potential, okay? This is the first quadrant, second, third, and fourth. So if you plot Butler-Warner equation, you will get something that looks like this. Okay? Now, in this particular case, the inflection point here is in 0, but doesn't have to be, because this is the potential scaling. We'll talk about it. But this is what the math and theory predicts, which means if I have a positive over potential, I will have positive current. Positive current is oxidation current, which means in terms of the deposition dissolution, we have dissolution here. Here I have negative over potential, I have negative current, and here I have electrodeposition. Okay? Now, whether this is clear or not, we're going to just do in a moment, but through the math. But what I want to remind you is that in our case, current density is equal to change current density multiplying e to the minus, e to the plus beta and f eta over RT minus e to the minus 1 minus beta and f RT minus beta, right? Now, if you look, what is important to appreciate, there is a minus sign here. When the electrochemical overpotential or overpotential, the way you define it, is negative, this is negative. This multiplies this minus sign, and all this thing here is positive. So we are talking about e to the x type of the functional for negative overpotential. Look here what we have. If this is negative, then whole this thing becomes like 1 over e to the x. Okay? What that really means, if I just separate these two and just look each of these separately, is that as long as I have a positive overpotential, which basically means that now this is positive, now this is negative, we can just think about is that the contribution of this anodic term and cathodic. Okay? You can see they cross here at 1. Okay? For 0. Because e to 0 is 1. Okay? Now, what is important also for you guys to appreciate is that why the current in our sign convention, because American sign convention is all reverse. That's why I keep telling you there's a Schmickler convention about this energy, symmetry factor, there's a bar, so literature is not unanimously transparent, right? People like to be inventive, come up with their own term definition, so on. As long as you understand what it really means and whether the grouping of the terms one way or another doesn't really matter. But what I'm trying to convey here is that obviously you can see that these contributions here in this range here, kind of we have to include both, and too far here and here, pretty much one of these terms will drop, right? So let's talk about the electrode position. If this is very large negative, this is very large positive, so we have this type of expression, and this type of expression goes to 0, right? So in reality, what you're really looking at, because this minus sign, the negative term is much, so E is equal I naught, and if this is 0, then minus e to the minus 1 over 1 over beta and f RT beta. Okay? Alright? This minus means the current negative. That's why we say the position for cathodic current is negative, because it's dominated by this cathodic term or cathodic reaction, right? In opposite, current is positive when it's dominated by this anodic reaction and this anodic term. So just vice versa, okay? So that's one thing. Now this important thing here is equal minus I naught E minus 1 minus beta and F over RT beta. It's called Tuffel approximation. So instead of writing the whole thing, you have a pretty good hint of the reality for larger potentials bigger than, smaller actually than minus 100 millivolts. This approximation is pretty good. You probably heard about Tuffle's law, which has been actually determined experimentally, right? Yet it represents this point. Now, one thing that is important is that when you do Tuffle, usually you talk about logarithm terms. That means that if the current is negative, you have to take absolute value of that current in order to logarithm to have any number. And then the logarithm will have to be absolute value of this and so on, but eventually I'm not going to go to this Mickey Mouse math, because logarithm of this equation you can play yourself, okay? So this is the Tuffle approximation, and it works very well when we are depositing in our potentials which have above minus 100 millivolts, right, values, okay? Meaning minus 2, 3, minus so on, okay? Now look at this again, this expression here. And you can see that if this is very small, and small means in a vicinity of 0, plus minus 10 millivolts, 10, 20, 30, right? But relatively small. Then if you know that around 0, any function could be expanded using Maclaurin's series, or if you want Taylor whatever, it's more general. Exponential function around 0, x, so e to the x is equal 1 plus x, if x is close to 0, right? Now, that x in this particular case applies to all of this, but you can do the math and figure out that this is really small, okay? And using the same terminology, e to the minus x is equal 1 minus x, right? So now in this situation when we are here, around this 0, over potential, maybe around here, we can actually use this conveniently, and then what we're gonna learn is called linear approximation. And that means that we can write this like current is equal I naught, and then multiplies here 1 plus beta and f over r d beta, and then minus 1, but then again, because just this term is 1 minus this, right? But with minus, it's minus 1 plus that, right? So 1 minus beta and f over r t beta, okay? Obviously this and this goes away, and this beta and this minus beta goes away, so what you're really left is I is equal I naught times, and what you're left here is basically just beta, and then this minus, basically it's going to be this and so on. But anyway, I can write this in terms of, okay, so let me just introduce something here which is more convenient in the literature. This term here is alpha A, and this term here is alpha C, right? And what we end up with is I naught alpha A plus alpha C, and f over r t here times a, okay? That's linear approximation, okay? I didn't have to use this alpha A and alpha C, but remember, we introduced this last time, and alpha A is anodic coefficient, and alpha C is cathodic coefficient, so we are not using beta, which is the barrier signature. Okay. All right, now, and we don't need this n here. Okay. All right. Now, interestingly enough, it looks like here that all this in a form is presented, because we have potential or over potential. Here's the current in a form that it is presented. It looks like that we see that this could be, because it's linear in potential, it looks like this is a proportionality constant, and this appears to be same as Ohm's law. Now, Ohm's law is basically that the current density is equal to, or actually, well, in electrical engineering, you know, it's basically that, let's say, current is equal to voltage over resistance, right? So, this means that this over here, we can write as 1 over, and we're going to call right now this term here, charge transfer resistance is equal to this term here, which is alpha A plus alpha C F over RT times over potential. Oh, excuse me, not either potential, just as it is, which means that RCT, or charge transfer resistance, is equal to, we just reverse this F, so it's going to be alpha A plus alpha C F, and here we're going to write RT, okay? Now, charge transfer resistance is sometimes very useful term to understand the corrosion. I'm not going to put much of the stress on this particular class because we talk about electrical position, but just for your convenience, sometimes in a problem, if it's charge transfer resistance discussed or something, that's what that really means. All right. Okay. Now let's do something else, which I'm gonna start. All right, I need to put a new board. Okay, if you remember last time, one of the results that we derived from the equilibrium, from the kinetics, is the equilibrium potential we discussed, which is equal to this term here, plus RT over NF times Ln, and then we get concentrations term, right? Do you remember that? Now, this thing here, importantly, is derived from the equilibrium conditions where we talked about surface concentrations and everything that is part of the electrochemical kinetics story. Now, we discussed also that this term here is a RT over NF ln Kc or Ka as well, if you remember. And because this doesn't have any concentration dependence, it's a constant. And it's basically, we call this equilibrium potential at standard conditions, and the standard conditions are when these guys are one mole or 1 mole per centimeter squared, whatever you want. Now that's important to discuss here because so you understand this is from the kinetics. So these concentrations here, as the kinetics gives you, represent surface concentration. Now that's not what we are used to in Nernst equation, which talks about concentrations in the solution of the pulp. Let's discuss that for a second, right? And I want to keep this for you guys relatively simple. This is our electrode, right? This is our solution. Now I have a concentration at the interface of some species. Now these species are three-dimensional with small molecules, but they have a thickness, which means overall that these concentrations on the surface presented in mole per centimeter square, if I divide with the final width of the interface, which is going to be called psi, width of the interface, I'm going to go from these surface concentrations, which I'm going to put here as for you, just 2 moles per unit volume. Usually what we like in electrochemistry is liters, right? So, or decimeters. So I'm going to put here liter. Okay? So from OH oxidized species, surface concentration, if I divide this by psi, I get OX, which can meter, and here we have units moles per centimeter square, okay? Do you understand that? So the interface width is the region where you don't have any more than what you have already on the interface, right? And that's how we can say now that this surface stuff we can replace, well, let's be a little bit practical. I can divide here xi, which goes here, and then this other xi goes here, so basically xi and xi will cancel each other, but it's not about that. It's like multiplying by 1, right? If I multiply this by 1, then instead of writing surface concentrations, I can write E equilibrium is equal E at standard condition equilibrium plus RC over NF Ln, and then I'm going to get here and then I'm going to put here bulk notation, just simply means bulk, which gives you idea that these are concentrations in moles per liter, okay? So that only is right that I just said to switch from this surface concentration to bulk concentrations, because we talked about equilibrium, right? Okay. Because that means that, you know, this width of the interface is the region that I can use and say nothing else here exists besides what is on the surface. And then I give a final volume to the interface. And you know, by the way, thermodynamically speaking, interface has its width. Okay, so you get this now that this is a real type of the nurse equation, okay? Okay, now what is really useful to discuss at the moment, what nurse equation tells us about equilibrium potential. So let's put this as a potential, and this is our equilibrium potential, and it's defined by this. Now, for the purpose of electric deposition topic, what you really need to understand is this concentrations here in a bulk solution are usually replaced with activity. Now, the activity of the bulk phase, which is basically the raw metal, is 1 by definition. So this term drops off, it's 1. So usually when we talk about reversible potential for the metal electrode in a contact with its ions, we really only use the expression that is talking about metal ions concentration. Because the bulk phase, as I say, activity-wise, it's 1. Okay. So this is our practical version of the nurse expression that tells you what's the equilibrium potential of your metal electrode in contact with its ions in terms of the concentration of these ions in the solution. If this is 1, this drops off, it's 0, and then you just talk about standard conditions, which is 1 molar solution. This is all tabulated in books for any metal you want, okay? It's calculated, it's there. What you really need to be aware is that depending how the solution looks like in terms of the concentration, the final value of equilibrium potential is not the same. Now let's discuss this. In practice, what we really like, not natural algorithms, or we like decade algorithms. Decade algorithm, natural logarithm is equal to 2.31 times decade already, okay? So if I do this kind of actually 2.31 natural logarithms, they equal, oh, am I right? Yeah, I'm right. Yeah, I'm doing this right. Okay. So if I replace this here, then I'm going to write that equilibrium potential is equal to equilibrium potential standard conditions plus 2.3 RT over NF, and I'm going to write the logarithm of NF plus concentration. And this is the typical form of the Nernst equation we are going to use now. What is really important for you guys is to appreciate if this is R is 8.4, T is about 300 kelvins roughly, Faraday constant is 96,500 coulomb, and so N. N is the number of the electrons transferred across the interface per unit for every ion that is actually charged, discharged. And so what you're really talking about, that there is some finite, and there is a 2.3, so there is some finite number here, and if you calculate this number, you can write that equilibrium potential is equal to equilibrium potential in standard conditions, and then plus, and you're going to write 60 millivolts divided by n logarithm of the concentration of metal ions in the solution, okay? Okay. So if this is standard condition, that means the solution has 1 mole per liter or ions, right? If solution is 0.1 mole, what I'm going to get? I'm going to get this potential, and if this is 0.1, logarithm of 0.1 is what?
-1.
-1. So it's going to be standard conditions potential minus 60 millivolts divided by n, right? So this is 0.1 molar per liter. This is 0.01 molar per liter concentrations. And this is going to be shifted negative direction because it's smaller for 60 millivolts over n, and here will be for 120 millivolts over n, or 180 millivolts over n, okay? So if I have an electrode in a solution with 1 molar concentration of ions, the reversible potential is, let's say we talk about silver, 1 electron, is about 180 millivolts more positive than silver electrode in a solution with 10 to the minus 3 molar concentration. That is very important because for many things we're going to talk about, but I'm introducing this to you guys just because I'm going to come back also to this form once again. But the point I'm trying to tell you is that there is a concentration batteries, right? If you have 2 compartments, for example, I'm just giving you an idea, which are connected by the cell bridge, and one is a copper 1 molar and one is copper 10 to minus 4 molar, and you have copper here, you're going to measure potential difference between these 2 copper leads, which is going to be how much?
240.
240 divided by 2, it's 120 millivolts, right? Get 0.1 volt just by having this difference in concentration. And so on. There's a lot of other interesting stories about it, but it's really important for you to appreciate how much solution controls the equilibrium. Controls equilibrium quite a lot. Now, having said that, I'm gonna tell you a little bit another story, which is something I wanted to tell you before, but but it could be also a matter of your homework, which I'm going to give you. So let's move on to, let me see if I have more. I wasted how many boards? So how do I get? I cannot write on that board that is behind, unfortunately. All right. Okay, so I have to erase one of these boards. Which one you can live without?
Probably the first one, the one behind both of these.
Which one is that? I only have one. I can probably get rid of this one, right? I can still write on this one too. Let me get rid of this one and then we're gonna continue. Alright. Okay, so what I'm going to tell you the story is about concentration polarization, which is an important thing. So we discussed how the Butler-Wolmer kinetics looks like, right? And let's say this is our potential here, and this is current density. But you know what the problem is? In reality, when we look, especially the position wave, the dissolution wave is okay. But when you look at the position wave, it doesn't go like this, but in reality it goes like this. And the question is why? Okay. The math of the Butler-Wolmer equation, which is somewhere it's on the top here, tells you that it's supposed to keep increasing as I'm increasing over potential, which happens with the dissolution as you have some self-ion precipitation, stuff like this. But here, what happens is that you keep increasing it, increases the current, keep increasing it over potential. Then at one point starts to kind of saturate, becomes constant, and eventually at this value of current, which you call diffusion limiting current density, potential or over potential shoots to infinity. So you cannot actually reach higher current density. Why is that? All right, so let's discuss again our famous interface solution. And so in equilibrium, which basically means eta is equal to 0 over potential, there's a metal concentration in the bulk. But since there's no consumption of metal ions, because there's no net deposition, there is an exchange current density, there is a deposition and dissolution happening at the same rate, but no net deposition. This concentration here that you have in the bulk is pretty much here. At the interface, right? Right next to the surface.
Now, if I'm going to approximate reality, an electrochemistry solution has a different type of, I'm going to say, properties next to the electron. And usually what that really means is that there's a layer next to the solid electrode surface, which we call diffusion boundary layer. And what that really means is that the solution next to the electrode surface is basically behaving like a laminar flow. So there's no turbulence, there's no stuff, even if you do, I don't know what, here, there will be certain thickness of the layer here that will only obey laminar flow, which means that concentrations or whatever, you know, that has to be transported from the bulk here have to occur by the diffusion, right? Now, the thickness of this diffusion boundary layer delta depends on the hydrodynamic conditions, could be smaller or bigger, but that essentially exists next to the surface all the time. And so, if I now change the over potential, but my kinetics is really, really slow. What it really means is that the ability of the solution to transport my ions to the surface is much bigger than what I can consume because it's a slow kinetic. Or maybe this is relatively close to zero, it doesn't really matter. I will still have a situation that concentration of the ions at the interface are close to the ones that are in the bulk, right? Like, but if my kinetics is fast, then I'm going to have a situation, I'm going to draw this here like terms of concentration. That here will be concentration at the interface. This is the diffusion boundary layer. Here's the bulk, the line concentration. So there will be a drop in the concentration of light because I'm consuming ions at a certain rate, and that rate that I'm consuming ions requires that there should be transport from solution bulk phase where concentrations are very equal across the boundary layer, the diffusion boundary layer, and so that we assume that this concentration profile is linear, which is not, but I'm saying this is approximation. And we can solve how much of this transport is happening is by saying, you know, if you talk about current, diffusion current is equal to minus NF. We need to include this to get the current, then diffusivity of the metal ions times, and this is dC over dx. It's a gradient of concentration in across the, let's say we call this x. Now obviously this is linear in our story, and so this diffusion current is minus NF dm plus times. How we can approximate this was but simply m bulk concentrations minus interface over delta, okay? That is going to be our diffusion current. Now, this diffusion current is equal to the current that kinetics consumed for basically material. And everything works out as long as you have this with some finite value. But if I keep increasing kinetics, I'm going to be dropping this more and more, and at one point, this will be zero. That will correspond to the maximum current that the transport through the boundary layer can conduct, regardless how fast kinetics you have. It cannot supply more ions, right? So this means that we have a limiting current density, which is based on the diffusion limitations. I'm going to call this IL minus NF d metal ions. By the way, this is diffusivity, you know, from the Fick's law, and then this is bulk concentration over delta, okay? That is this current here. see that? This is the diffusion limiting current. Now, is there any way that we can fix our PV equation to accommodate for these transport limitations? Because obviously this is reality. If I want to fit this reality with PV equation, I might be okay up to here. But here, no way. So, usually, transport limitations are something that should bother us as the higher work potentials. But you know, that also depends, you know, whether the viscosity of the solution is high. Especially if you work in ionic liquids, you know, viscosity is way higher than water, for example. Temperature plays, you know, role as well. And so there's a lot of things that can actually make this boundary shift up and down depending what really you're doing, okay? And that also depends whether this diffusivity here of the ion in a what? Is it in ionic liquid? If it's in a polymer, like in a battery, there's a lot of different things, you know. So the transport for by diffusion is actually, in terms of the, I'm going to call this kinetics of the diffusion, but it's not kinetics because it's a transfer. It's, you know, reflected in this diffusion coefficient of the metal line. Okay. Okay, so can we fix it? Yes, we can. Let me give you an idea what we can do. Now let's just see what I'm going to do with the real estate. So I can keep this, then I can bring this down. All right. So for your information, these are concentrations. This is X. This is delta. When you have equilibrium, as I discussed with you guys, and that's the same equilibrium we talked about when we were driving Butler-Warmer equation, if you remember, when we said rate A is equal rate anodic rate is equal rate cathodic, that happens at some potential, which is equilibrium potential, and then we did all that thing, you know, and eventually got to the expression. We do assume that basically here is bulk at the interface, and it's same as is here. But when I have some kind of a over potential, then here will be M interface, and this is different than the bulk, right? Basically, I'm restating this here, okay? Now, what is really important right now, in this potential scale that I have shown here, is to appreciate two things. If you remember when we talked about equilibrium, we looked what is next to the surface, and it was equal to 1 in the bulk because we didn't have a net flow of the material, not a net deposition, right? Now, here in this situation, when I start having deposition, so flow, net flow is this. What happens with my equilibrium potential? Because at that surface, suddenly, concentrations drop, right? If they drop, what happens to my equilibrium? We're not talking about equilibrium, but what's the equilibrium potential of the concentrations if we would have the same, you know, equilibrium but different? Now, what would be equilibrium at lower potential, or lower concentrations? It would be different, right? So in our Butler-Warmer equation, we have E is equal to E naught, And by the way, I'm not gonna talk about whole Butler-Borman equation. We're just gonna take conveniently Taylor approximation. Basically, minus I naught e to the minus 1 minus beta and f over r t. This is eta, right? Over potential. Let's say, I'm just trying to explain to you what happens. With respect to the equilibrium, when we didn't have any net rate, my equilibrium potential was here, and I applied over potential eta here, right? But because the concentrations at the surface changed and dropped to, let's say, 0.1 mole, my equilibrium potential with respect to this concentration interface also changed, right? So that means that my effective over potential is reduced for this value here. I'm going to call this delta E equilibrium, right? So my effective over potential is equal minus delta minus D equilibrium, okay? Do you guys see that? Let's calculate delta EQ. Well, delta EQ here is equal E naught plus RT, and then here will be M and plus concentrations, which are the interface, right? So this is prime, and the regular E equilibrium is equal E naught plus RT, and this is going to be ln, sorry, not that L, not ln, sorry. Let's just test out this. RT over NF. I'm going to use the ln version, M plus at the interface, and here it will be RT over NF, ln, M plus at the bottom. So the difference between these two, I'm going to call them just delta E equilibrium, is equal to EQ prime minus EQ, or equilibriums. Delta EQ is equal to, if I subtract from this one, this cancel out, this cancel out, and what you really end up with is just this term RT over NF ln, concentration of the metals ions in the interface divided by concentration of the metal ions in the bottom. Okay? You see that? So that shift due to the depletion of the metal ion concentration at the interface causes that the real overpotential is reduced, right? And this real overpotential is reduced for this. And that means we can call this concentration overpotential, right? Because it comes from the fact that we are doing depletion of the metal ions near the interface when you start running deposition. Okay? Now bear this in mind because this is still far from over. I'm going to go now, continue on this board here. And start from here. Peter, you really did a good job, I must admit.
Yeah, I clearly did
Right.
it.
So we're gonna neglect the anodic part, so we are going to double approximation, which is basically E is equal to minus I naught times e to this, right? And so now we have to adjust for this eta minus eta concentration, because the potential that we think we have is not the same, right? So let's do this. I is equal I'm going to just put minus I naught e. The minus is going to be minus 1 minus beta and f over RT eta. And then this minus times minus is going to be plus, so this is going to be e to the eta c, right? Now, eta c, I just told you, is equal to RT over NF ln metal concentration at the interface divided by metal concentration in the bulk. So when you put this here, you're going to have this multiplying this, and so it's going to look a little bit messy. Let me just continue here. So current is equal minus I naught e to the minus 1 minus beta and f over RT eta times actually here I just forgot to write this whole thing minus 1 minus beta and f over RT, right? And so when I put this here, it's going to be 1 minus beta and f over RT multiplying RT over NF, and then ln, and then metal concentration at the interface over metal concentration in the bottom, right? And this thing you know already, and here we have to get rid of this and that. And then what we have left is this 1 minus beta. When it goes on the logarithm, it's going to be all this to 1 minus beta, okay? But then because e to the logarithm, what we are left is just this, right? So the final thing is minus I naught times mi over m bulk over 1 minus beta times e to the minus 1 minus beta and f over r t times a. All right? Now this expression now does a job. With here experimental data that I explained you how it looked to model it. Now let me tell you how this really works. We're not done yet, but this is the key thing. You can see that here, as this goes down, let's say beta is 0.5. Let's say, that means there's some kind of exponent less than 1 here, right? So let's say this mi is only 10% of the bulk concentration. This ratio, square root of 0.1 is 0.03, something like 33, right? So that already, just because of this depletion, reduces, because this is very exponential factor, it reduces significantly this value of current density for whatever potential you have that generates this current, that generates this, right? Okay. So let's kind of make it a little bit more transparent in terms of current. If you look our diffusion equation that we discussed, I said that the diffusion current is minus NF D times C M concentration at the bulk minus M concentration at the interface over delta. But I also said that the limiting current density is equal to minus NF D and then F bulk over delta, okay? If you play with this, that's trivial math, I just don't have enough space to do that. You can show the ratio of M concentration in the interface divided by the concentrations in the bulk is equal to one minus I over I L. It's very easy to show this. This is the current that you can transfer by diffusion when concentration interface are not zero. This is the maximum current, I limiting. And so if you can do that, that means that we can finally write the Butler-Over equation, which does the job for transport limitations, to be like this. I is equal minus I naught times 1 minus I over I limiting on power 1 minus beta e to the minus 1 minus beta and F over RT eta, okay? So this eta is defined with respect to the equilibrium when, true equilibrium when we discussed when we have this interfacial concentration equal to the bulk because nothing really happens and so on, okay? So that's pretty much the end story, okay? And so you can see right now that the closer this becomes to IL, this is becoming close to 0, to 1, and this whole term comes close to 0. Now, when you think about simply how the math works in terms of what really happens in the system, is that let's say this is our eta, and this is the value of limiting current density. So for the small overpotentials, nothing really truly affects the concentration at the interface because the kinetics is very small and the transport really supplies more or less everything that is needed, right? And so this really looks like a PV equation in the very beginning. Then this starts to grow maybe 70%, 30%, 40% of this value. 1 minus 0.4, 0.3, it's point something, and then square root of that term already for the given addition in overpotential that you expect to get somewhere here, because this term here minimizes. So this would be original PV equation, right? But because of this term here that multiplies now and reduces the overall current, right? You actually start to see something like this. But then this becomes really close to, it means, you know, I increase for more, I expect to be here, but this term levels this up. The closer we become in the current to the value of IL, right, the more dominating math comes from this term instead of this term. Eventually, you can increase as much as you want, your potential, the current will not be increasing at all, right? So then you're at the limiting current. Okay. So this is how this works. Now, unfortunately, what you see here is that this is not equation that is in explicit form, because you have current here. But it doesn't matter because you can fit your data with this type of a form if they're given to you, and you can extract constants of the fit, which is I sub L. You can extract this whole term and this term and so on, right? So that's really the point, because numerics, you know, allows you to use this for fitting, but you know, as an explicit form, if I tell you, for example, the overpotential is this, there's no way you can come up exactly with, you will have to, you know, trouble, you know, keep one number, calculate and see what you're getting, the overpotential. If you solve this for overpotential, you will see it's an interesting thing that will be part of your homework as well. Because if you solve this for overpotential as a function of current, then you're going to see clearly two terms, right? One will be term that is a part of the overpotential driven by the kinetics, or we call this activation polarization. One will be, that is driven by the concentration polarization, which is NC. And, this is going to be part of your homework. But anyway, do you guys have any questions? All right. So everything we talked today will be, is recorded, will be on the, available to you tonight. You have your homework. And so, if you have any questions, you can always schedule, the, face-to-face meeting with me. I don't expect any problems. Everything we talked so far, you can find in any electrochemistry book, but I'm trying to kind of decipher this to a language which is more acceptable for you guys, right? And then it's going to be more and more interesting as we start talking about some real stuff. So next week we're going to talk a little bit about double layer, and then we're going to talk about absorption and some other things which are important. And then eventually we're going to be doing some other stuff. Okay. So any questions? All right. That's it for today. Thank you.